In this series of talks, we're going to look at the process of optimization, of trying to make our program optimal in some regard. Optimization's important, as we mentioned previously. The two common ways that we can try to optimize our program is that it uses as few a number of CPU cycles as possible, it runs as fast as possible, or it uses as little memory, it's a small memory footprint, as possible. We also mentioned that these tend to be mutually exclusive in as far as if you're trying to optimize for speed, some of the techniques you can use to do that can involve adding in extra data, increasing the memory footprint, and vice versa for optimizing for the memory footprint. Why is it important to optimize? I mean, obviously, if we're thinking about speed and we're thinking about, say, writing a game or whatever, we want it to run as fast as possible. Beyond that, there's a couple of other good reasons. If we are writing something that is fast, then it is providing a better user experience. Things are responsive, they happen more quickly. Also, incredibly important nowadays, given the prevalence of mobile devices which run from batteries, which have a limited amount of, if you like, time available to them. If we write a program that is efficient, that runs fast, then it'll put the minimal amount of drain on the actual device itself. And that's good, again, in terms of power usage, in terms of user experience, and a whole host of other things. So optimization is a really key component that we should certainly strive by way of introducing into any of the programs that we write. We think about efficiency, again, it's just mentioned here, it could be CPU cycles, could be memory usage. One important thing to note is that you can have a process that is optimally fast, but for that process still to be very slow to run. And again, this ties into the notion that for some algorithms, for some problems, for example, NP complete with large data size, there probably just is a large volume of processing that needs to be done. And short of going for something radical like a quantum computing solution, there can be some processes where there just is a lot of computation that we need to blast through. And even if we do it optimally, it may still take time. So we're going to, in terms of the optimizations that we're looking at here, primarily focus on speed, trying to get it to run as quickly as possible, to use the smallest number of CPU cycles as possible. If we want to, in this lecture, we're just going to simply introduce some of the high-level aspects of it. There's two ways we can try, there's two broad areas into which we can try to introduce optimization. They are design time, and then also when we're coding it for more of a runtime aspect. So we can think about, from the design's point of view, how do we create a model that we feel is going to be fast and efficient. Generally speaking, it's language independent at the design time. Also, generally speaking, the decisions that we make then have the greatest impact on the overall performance. So if we get it right at design time, it's going to be much more easier to get high performance. If we get it wrong, then it's likely to be, no matter how good our coding or implementation is, high performance will be an elusive aspect. Coding efficiency is the other aspect in terms of, given a design, how do we actually implement that within code? This is done at the level of what we write, level of blocks, level of units, looking at the process of compilation, looking at the actual hardware device in which we are running. Now, we can break these down somewhat. So we're thinking about design time efficiencies. There's two broad categories that we can subdivide design into. The first one are the algorithms and the data structures that we select. So we will have a particular problem or something that we want to accomplish. We can choose or create an algorithm to do that, and the data that we're manipulating will be in some form of data structure. So for things, for example, like searching or sorting, the algorithm can have a significant effect. Depending upon how the data is accessed, if it's linearly, at random, if we can add or remove or restructure the data, the choice of data structure that we have will probably have a strong influence on just how quick that process can be. Alongside that, another design time aspect is actually the program structure itself. So here we're thinking about how we have decomposed it into different layers, different classes, the object hierarchies, how communication passes between these, And again, if we have a design that has multiple layers or information has to flow through or can't get quickly from one point as needed to another, then that will introduce delays or bottlenecks in terms of our overall optimization. If we then move down to looking at coding efficiencies, there's a few areas here. First one on the left hand side is language constructs. So the actual programming language itself will give us a number of constructs that we can use. This comes down to how we actually code the thing itself. The actual architecture in which we run is highly important. So knowing how many cores are available, what sort of cache is available, of what size, at what level, and structuring our program to make good use of this, again, will be a factor that will determine how fast it runs on that particular platform. Use of libraries. So we're not really here talking about reinventing the wheel in most cases. We'll want to make use of built-in libraries. In doing that, we want to be slightly cautious about the performance of those libraries. Generally speaking, they're good, but we want to test our assumptions, or we may want to use a third-party library that we know offers a particularly fast implementation of some particular area or function. Last one here is the whole notion of compiler optimizations, or introducing in optimizations themselves. As we mentioned, the compiler will try to do this. We can use a good compiler. We can get better optimizations if we write our code well in a simple structure. It can help the compiler. We may want to then go and add on a few optimizations ourselves. So a whole bunch of things we can go down at the level of coding that can help improve the performance. Key takeaway from this is that the design choices that we're going to make when we're designing something, they're going to have the greatest impact overall on the efficiency of it. But if we want to have something that is truly optimal, we can't ignore the coding aspect. We must also make sure we have coded this in an optimal manner as well. So real efficiency comes from the union of these. A good design with a good implementation, we are then likely to have an efficient program. And that's it for this introduction. Takeaways from this, really to point out that the design time choices, they're the key things. We need to get those right first of all, or at least think about performance at that level. And if there are things which are really critical in terms of their overall performance, we need a good design and a good implementation. And we may find ourselves in a position where we're looking at the code that we've written and asking how can we make sure this runs optimally as fast as it possibly can. Later talks in this series will delve into some of the coding implementations in more detail. We're not really going to be concerned here with the design time aspects in terms of data structures and algorithms or looking at the object hierarchies. We're going to be more concerned in these talks about implementation specific ones. But as a final reminder, it's the design time stuff we need to get right first of all.